Alright, in this video we're going to talk about section 5.1, which is called distance and accumulated change. So suppose we're given the following velocity graph. So we have some kind of object that's traveling at a speed of 15, and let's go ahead and say it's miles per hour, just to make things easier. So how can we go about finding the distance this car, let's say, traveled during the first 10 hours in this situation? Well, since it's traveling a constant velocity, we can essentially find the distance by calculating the rate multiplied by the time. That's usually how people remember that. Distance is rate times time. So the rate here is our velocity. So it's technically velocity times time, but usually people will refer to it as the rate. So essentially the distance this car is going to travel in those 10 hours is going to be that 15 miles per hour times 10 hours, so 150 miles. Okay, so 15 miles an hour for 10 hours, you're going to travel 150 miles. Now we're going to come back to this in a second, but let's think about what if the function changed, and now it doesn't look like a constant 15 miles per hour, but instead it looks like this. Now I know that this graph is a bit wonky because it starts at 4 instead of 0. Let's just pretend that doesn't happen. But we have this function now, so we have some kind of magical thing that can change velocity instantly. So we essentially have that in the first 5 hours, it's going to travel 6 miles per hour constantly. And then for essentially the next 5 hours, from 5 to 10, it's going to travel at 10 miles per hour. So what if we wanted to find the total distance traveled by this, whatever the heck this is, over those 10 hours? Well, we'd have to kind of break it up because we have these two pieces. We have the first part where it's traveling 6 miles per hour and the second part where it's traveling 10. So we could find out how much it travels in each piece. So we could say when it's traveling 6 miles per hour and it's doing that for 5 hours, well, then they must have traveled 30 miles in that 5 hours. And then if they start traveling 10 miles per hour, and do for another 5 hours, so we're going from 5 to 10, so it is still 5 hours, well, that must have been 50 miles. So then the total distance they traveled must have been 80 miles. Okay, so when we're traveling these kind of constant velocities, it's not too bad to figure out how far we've traveled over that time. Now, can we notice any type of relationship between the distances traveled and the graphs? So let me zoom out a little bit to get both of these in here. So we had the first one, we had a constant 15 miles per hour for the whole entire time, and then the second one, we essentially break it up into two pieces. And is there some kind of graphical representation of these values, of this 150 miles, of the 30 miles, of the 50 miles? Does it actually somehow show up on the graph somewhere? And so if we think about what we're actually calculating in this first example of this, constant 15 miles per hour, what does the 10 and the 15 actually represent here? Well, if you think about, our x values here, that's spanning over a course of 10. And then here we have our y values are going up to 15. So if we're breaking this off at 10, because we only care about how far we've traveled in 10 hours, essentially, what does 10 times 15 actually mean in terms of this rectangle, when that 10 times 15 would end up being the area? So essentially, what we just found is equivalent to the area of this rectangle. So that rectangle has an area of 150, which is equivalent to the amount of miles we've traveled. And a similar way in the next one where we broke it up into two pieces, we're essentially finding the area of the two pieces. So we have 5 times 6 gives us the area of the first rectangle, and 5 times 10 gives us the area of the second rectangle. So we're still finding areas here. So then the question becomes, if this distance traveled is actually equal to this area, can we extend this a bit further? So what relationship do we notice? We notice that the distance traveled is equivalent to the area underneath the function. So let's say we extend this question to what if the velocity is given by the function y equals 5x? So it's no longer a constant velocity, it's constantly changing over time. Every single second it's a new velocity. So we can't really do the distance equals rate times time in this situation because the rate is constantly changing. But if we think about it in this new way of area, if we block this off and say we're trying to, again, find the distance we've traveled in those 10 hours, well, if you think about what shape we've essentially created, that blocked off area is a triangle. And we can easily find the area of a rectangle if we remember the equation. So the area of a triangle is 1/2 base times height. So in this case, our base would be 10 and our height would be 50. So we can say that the area of this rectangle is 1/2 times 10 times 50, which would give us 250. So if we're saying that the distance traveled, if this is a velocity function, is equivalent to the area underneath of that function, then the distance traveled is 250 miles. Okay, great. So now if we have a velocity function, we can figure out how far we've traveled if we just find the area underneath of the function. Awesome. Well, what if the function doesn't give us a nice shape? So, there are tons of functions that don't turn into rectangles or triangles or trapezoids or circles or, shapes that we actually know the area of. So, what if it's not a nice shape? So let me zoom back in a little bit here. What if it's not a nice shape? So let me go ahead and draw I'm going to try to make it the same graph. So I'm going to try to make both of these the exact same graph. Of course, they're not going to be perfect, but let's say we had a function that looks like this. And let's say that this is still some velocity function. And say we want to stop right here. We want to figure out how far we've traveled in that time frame. Well, I would really like to find, whatever this area is in here, but that's not a shape that I know the area of. It's not a circle, it's not a square, it's not anything that I'm used to working with. So how the heck am I going to be able to figure out the distance if I can't find the area? Well, at this point in time, we're going to figure out something in a few more class periods from now, but what we're going to start with is we're going to start by estimating. So we're going to be able to estimate the area underneath of these functions. And the way we're going to do that is we're essentially going to break these functions up into a couple of kind of sections here. Let me see, how many do I have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I've broken this function up. Again, I have two tried to be the exact same function here. So what we're going to do is we're going to essentially use known shapes. So we're going to use known shapes. The easiest shape to find the area of that we know of is essentially a rectangle. So let's essentially break this up into a bunch of rectangles. So we're essentially going to impose a bunch of rectangles on this function. So the rectangles are going to have width of, say this is 1, 2, 3, 4, 5, 6. You know what, let's even make it let's step it up a little bit and let's make it up by 2. That might demonstrate it a bit better. So let's say it goes 2, 4, 6, 8, 10, 12, 14. So if we were to break it up in this way and it was broken up into essentially pieces of 2, the width of all of our rectangles would be 2. So essentially we'd be taking the rectangles to be kind of in these pieces. So we're breaking them up. We're essentially breaking the function up into these kind of sections that are kind of width 2, if you will. And we'll do the same on the other picture as well. So now the question becomes, what is the height? What is the length, whichever you prefer to call it? I'll call it the height here because I think that makes a bit more sense because we're going up to the function. So what height are we going to choose for our rectangle? We can't have more than one height, but we have like this whole entire piece of the function in that first interval that we could choose from. What height are we going to choose? In general, you could choose any of them. But specifically, we're going to be consistent. We're going to choose either the very leftmost point or the very rightmost point. So say I want to go about choosing the very leftmost point, the very rightmost point. So say I'm doing the left first. So I essentially have this first interval, if you will, between 0 and 2. So the very leftmost point is going to be at x equals 0. So I'm going to pick that y value, and that's essentially the height that I'm going to use to form my rectangle. And then my second interval is essentially from 2 to 4. So the leftmost point is 2. So I'm going to take the y value at 2, and I'm going to use that as my height of my rectangle. Same thing, from 4 to 6, I take the value at 4, and I use that y value as my height. And then the height at 6 for my next interval, and so on and so forth. The height at 8, and then the height at 10, and then the height at 12. And our last interval is from 12 to 14, so I use the leftmost point, so 12. So essentially the y value at 14 doesn't get used here. But essentially what we would have then is we would have a bunch of values that we would know because we would actually know the function here. So here we don't have the values because this is just a generic setup, but we would have those values or be able to calculate them, and we'd be able to then find the area of all of those rectangles and add them up. What if instead we wanted to use the right side? So it's going to be very similar, but so if we start going from 2, 4, 6, 8, 10, 12, 14, so our first interval is from 0 to 2 again, but now instead of using the left, we're going to use the right. So we're going to use the y value at x equals 2. So we'll use that value as our height for our rectangle. And then from 2 to 4, we're going to use the y value at 4. From 4 to 6, we're going to use the y value at 6, and so on and so forth. So in this case, the very last interval is from 12 to 14. So since the right point of that interval is 14, we're going to use the y value at 14. So essentially in this case, there's one point that we don't use, and that's the y value at 0. So now notice that these won't necessarily find the same value because they're completely different rectangles. But these are two different approximations of the same area. And remember, as I stated a little bit before, these are going to be estimations. They're not going to be perfect, but they are going to estimate the area for us. So this is the idea that we're going to build upon in the next video or two, is how to find these, areas, these sums of these areas of these rectangles. Now, these are called Riemann sums. So if you ever hear me say Riemann sums, this is what I'm talking about, where we're breaking something up into a bunch of rectangles and adding up the area of the rectangles. So at this point, we haven't done an official example yet. We'll do that in the next video. We'll go ahead and stop this one here, and in the next video, we'll see how we're actually going to use this on a full example.